So hi everyone, my name is Adrienne Maria Such and I'm a second year PhD student at Trinity College Dublin. And today I would like to talk about the replacement of calcite by rare earth carbonates, especially focusing on the formation of bastnäsite. So rare earth elements are key to all modern and near future technologies. They have especially high importance in green energy and military technology. We use them in magnets, lasers, batteries. They're pretty much all there in every personal electronics, so phones, tablets, laptops. Whatever you're watching this presentation, it's sure it has rare earth elements. So there is a really huge demand for rare earth elements, which is continuously growing. But where are we getting them? So the three main sources of rare earth element currently are bastnäsite, monazite, and xenotime. And in our experiment, we focused on bastnäsite. So why are we studying bastnäsite and what are the difficulties we are facing when it comes to rare earth elements? So rare earth elements are more abundant than many of the platinum group metals. However, finding a mineable deposit with concentration high enough for economical extraction is quite challenging. And even if we have the mineable deposit, separation of the rare earths are very difficult. And when we turn to recycling, it can be more complicated and it can come with even greater environmental harm than mining itself. So what we can do is trying to gain a better understanding of the biogeochemical cycle that describe the movement of rare earths through lithosphere, hydrosphere, and biosphere. And as well, we can try to gain a better understanding of the main geological processes by which minerals containing the rare earth elements and other critical matters as formed and concentrated. So the main purpose of the study was to mimic potential recrystallization or replacement reactions involving calcite in rare earth deposits during hydrothermal and metasomatic processes. So in this study, we carried out a heterogeneous experiment. We worked with lanthanum, neodymium, and dysprosium-bearing solution, and we simply added calcite crystals to these solutions. So this way, we could see what happens when rare earth-bearing solutions interact with calcite. And we follow this reaction at different temperature. So what happens then that the carbonate and calcium ions dissolve into the rare earth-bearing solutions, especially close to the calcite crystals, and react with the rare earth ions, forming rare earth-bearing carbonates on the surface of the calcite grains. So on the right side of the slide, you can see that this new rare earth carbonates phase forming on the surface of the calcite, and with time the entire calcite grain is fully replaced by the rare earth-bearing carbonate phase. So we were doing intervalling sampling, so we could take calcite grains out of the solution, thus we could have a look at the reaction with XRD. What you can see on the left side at the bottom is calcite, that is day 0, and the top of the figure you can see calcite neodymium fully replaced the entire calcite crystal at 50 Celsius by the end of the day 11th. So repeating the same experiment at different temperature, a reaction pathway started to show itself. So these new rare earth-bearing carbonate phases follow the crystallization sequence from calcite through lanthanite, calcite, all the way towards the most stable phase, bastnäsite. Which exact phase occurs, how fast and when, were found to be strongly dependent on the temperature alongside with the ionic radii of the rare earth elements used in the solution. For example, at 50 Celsius, in a lanthanum-bearing system, lanthanum forms within a few hours, and about 10 days it turns into calcite, and an extra few weeks and it's going to turn into bastnäsite. Meanwhile, if we go into a neodymium-bearing system, it's a bit slower than the lanthanum-bearing system. It takes about a few days just to form the neodymium lanthanide. And if we go into a dysprosium-bearing system, it's even take longer just to start the reaction. It's need about a few weeks to begin the nucleation. So we find that with raising temperature, the speed of the crystallization can be increased. So for example, if we look at the figure, we see that at 220 Celsius, in case of lanthanum and neodymium-bearing system, bastnäsite can form immediately, and it only takes about 24 hours. But here it should be highlighted that there's no such a thing as dysprosium bastnäsite. And the reason for this is the difference between the ionic radii of these elements. So out of these 3 elements, dysprosium has the smallest ionic radii. And with this size, dysprosium is just simply not capable of building a stable enough structure to form bastnäsite. But ionic ruddy is also responsible for the speed of the reaction and the exact impact of the temperature. So what I mean is that smaller the ionic ruddy is higher the ionic potential of the element. And higher the ionic potential, the higher energy needed to remove the solvation layer of the ion, and hence the higher the temperature or the longer the time that is required for the crystal nucleation process to begin. So this is also the reason why we could not observe epitaxial overgrowth in case of dysprosium systems. So by the time dysprosium started nucleation, because of this longer time, more carbonate ions can dissolve into the solution, raising the supersaturation level, especially close to the calcite grains, surface of the calcite grains. So compared to lanthanum and neodymium bearing system, dysprosium started nucleation a lot later, but it will start growing also a lot more rapidly with the higher supersaturation level, so resulting in a larger number of orientational defects. And this prevents dysprosium to form an orientated overgrowth on the surface of the calcite grains. So in the figure you can see in A and B images, lanthanum calcite and C and D neodymium calcite with an epitaxy on the surface of the calcite grain. And in case of E and F, you can see dysprosium calcite with no orientated overgrowth at all. So there's no epitaxy has been observed in case of dysprosium. So in summary, bastnäsite can form directly from solution and also via replacement of calcite. It can follow a very complex crystallization pathway driven by the ionic ruddy of the rare earth element present in the system and the temperature. So these findings are relevant for understanding of mineralization reactions occurring in rare earth bearing metasomatic replacement bodies. And also, it's relevant for the synthesis of rare carbonates with tailored structures and chemistries for the production of new innovative materials. And with this, I would like to thank you for your attention. I'm happy to answer any questions, even now or later on, or you can just scan the QR code and it will lead you straight to the paper about this study.